Good morning, class. Today we're going to continue our look at transcendental functions. In our last class, we concentrated on the derivatives of sine and cosine, and I'd like to just extend that to these other trigonometric functions: tangent, cotangent, secant, and cosecant. So we're going to concentrate on these first 6 derivative rules. A reminder that we also have a few trigonometric identities listed to the right on our page. The first 3 are just for the reciprocal functions. This one says that tangent is sine over cosine. And you should note here that since cotangent is the reciprocal of tangent, it means that cotangent would be cosine divided by sine. So cotangent is the reciprocal of this fraction. That's why it is cosine divided by sine. Just our derivative rules from Unit 1 at the bottom of the page as well. Okay, so let's go through these problems together. We have y is 0.5 times the cosecant of 1 minus 2 pi t. So we must consider the argument or the angle to be 1 minus 2 pi t. So we're comparing this to cosecant of little u. So right here, this is our little u. Okay, and so if u is 1 minus 2 pi t, then what is its derivative? So the derivative of u with respect to t would be 0 minus 2 pi times 1. So it would just be negative 2 pi. Okay, so we're looking at the derivative of cosecant of u. So take a look at number 6, cosecant u. Its derivative is negative cosecant u times cotangent u times, in this case, du by dt. So I'm going to write negative cosecant u times cotangent u times, and this is where we will have our negative 2 pi. Okay, so this is informing y prime. So 0.5, of course, is multiplied out front. So negative 0.5 cosecant of u times cotangent of u times du by dt, which is negative 2 pi. Okay, so I can try to keep this off to the side here by a little division line there. Okay, so when we rewrite this, of course, these angles or arguments do not change. So the negative 2 pi here at the end can be multiplied by the negative 1/2 out front to give us y prime equals, so we'll get positive 1 pi. Positive 1 pi will be in front of the cosecant of u times the cotangent of u, just like that. Okay, so we had to identify what the argument was. We had to take its derivative with respect to the independent variable. And that is this ending piece in the formula. Okay, so let's try this other one. We have y is 9 times the cotangent of 3x squared. So this now becomes the argument of the function. So the little u is 3x squared. So what is its derivative? It'll be with respect to x. That would be 6x. So now we just use the correct formula, cotangent u. So let's look at that formula. Okay, so the derivative is negative cosecant squared of u So same angle. And then here is where we're going to multiply by du by dx, which we just worked out to be 6x. Okay, so y prime is, now it's negative cosecant squared of u. So negative 9 cosecant squared of 3x squared times du by dx is 6x. Okay, so negative cosecant squared u times the derivative of u. And anytime there's a constant, it's just remaining out front as a multiplier. So in the final answer, again, this 6x would never be multiplied by 3x squared. The angle will not change. 6x instead can be multiplied by negative 9 out front. Okay, final answer looks like that. Now, the difference with problem 3 is the cube right here. In number 2, only x had the exponent of 2. But in this question, remember, this means that the whole secant function is cubed, which means that in order to differentiate this function, we are going to use the chain rule. Okay, so when we use the chain rule, remember, we're going to do the exponent part first. So what does that mean? It means this 3 comes forward. The inside of the bracket stays the same, and the new exponent will be a 2. That is then multiplied by the derivative of the inside of the bracket. So that's how the chain rule always works. Whether it's an algebraic function, like if we had a binomial in here, something like 5x squared plus 2, we would use the chain rule. But it also works for these transcendental functions. So we do the exponent portion first. Now we have to multiply by the derivative of secant 2x. So what will be the derivative of secant 2x? It will be secant 2x times tangent 2x times the derivative of 2x, which is 2. Okay, so our little u this time is 2x. Secant 2x has a derivative of secant 2x times tangent 2x times 2. So that will all be here. Secant 2x times tangent 2x times 2. So all of this is the derivative of the inside of the bracket. Okay, so in writing our final answer, the 2 is multiplied by the 3 out front. Now look, we have secant squared times secant. So this becomes the secant of 2x all cubed. And then we will also have tangent 2x, like that. And it's fine to leave it like this. If you prefer, you can write it this way. 6 secant cubed 2x tangent 2x, right? So we can do that instead. And then it would resemble more closely the original, but I was perfectly content with the answer here as well. And one last thing, you could take this tangent 2x and write it right after the 6 instead, and that would also mean the same thing. Okay, let's look at number 4. Now, in fact, there are a number of ways to form the derivative of this function. You could, for example, use the quotient rule. But if you use the quotient rule, the derivative of u, the numerator, would be 0. So that's a bit of overkill. The other thing you could do is rewrite this so that sine 3x has an exponent of -1. Right, so it could be written 7 times the sine of 3x all to the -1, and then you could use the chain rule. And the last way to do this, though, is to use this trigonometric identity, the fact that 1 over sine is cosecant. See, because right now this means 7 times 1 over sine 3x. So that means it's 7 times the cosecant of 3x. So that's the original function y. So then, in forming y prime, all we have to do is form the derivative of 7 cosecant 3x. So, right here, cosecant 3x has a derivative of negative cosecant 3x times the cotangent of 3x times, this is the derivative of 3x, which is 3. Okay, so it's 7 times negative cosecant 3x cotangent 3x times 3. Okay, the derivative again of cosecant 3x is here. Negative cosecant 3x cotangent 3x times 3. Okay, and in writing our final answer, we would take, this is negative 7 times 3. We would have negative 21 in front, like that. Okay, so that's a very good way to do this problem, just by using the identity that 1 over sine is equal to cosecant. All right, let's try this question. So kind of comparing it with number 3. In number 3, we ended up with the whole secant function cubed. This, of course, is the same as this. So this is the argument u, or this is the argument u. We have secant of u right now. So we're going to be using the chain rule only when we form the derivative of u. All right, so overall, this is considered just a plain old secant function. While overall, back here, we had a chain rule. Okay, so let's try this. So what I mean is that when we form y prime, we begin by doing what is the derivative of secant u? Well, it's secant u tangent u times the derivative of u. So secant u times tangent u times, now here we need the derivative of u with respect to x. Okay, so secant of u, tangent of u times the derivative of u. Now, how will we form the derivative of u? That's where we need the chain rule. So let's do it here. Secant u, tangent u times, okay, now in forming the derivative of u, we use the chain rule now. Okay, so maybe I'll just put chain right here under du by dx. So in other words, start with the exponent 1/2 forward. The new exponent is -1/2. And we have to multiply by the derivative of the inside of the bracket. And what is the derivative of 1 minus x? Well, it's 0 minus 1. So we end up with -1. So all of this, right here, all of this part is the derivative of u with respect to x. So we use the chain rule to differentiate u. Okay, so this whole thing becomes our derivative. Again, secant u, tangent u times the derivative of u. So how can we rewrite that? Well, this negative, well, it's like a negative a half, right? It's like a negative a half. And then we'd have this, oops, sorry. I'm gonna try this again, okay? Because we're gonna have a numerator and a denominator here. So maybe I'm gonna do it like this instead. And the reason I know we're going to have a denominator is because this guy has a negative exponent, right? So that means we can drop it to the denominator where its exponent would be positive half. So we have 1 minus x to the positive half in the denominator. So maybe I'm going to start with that. Okay, so there that went to the denominator. The 2 is also in a denominator, 1 over 2. So I'm going to put the 2 down there as well. So what's left for the numerator? The negative 1 and also the 2 trig functions. So secant 1 minus x to the half and tangent 1 minus x to the half, just like that. Okay, so again, this gave me the 2 in the denominator. This went to the denominator. The exponent is positive. Negative 1 is left in the numerator with the 2 trig functions. And of course, in the final answer, we could change all of those to square root signs. Right? So 1 minus x, 1 minus x, 1 minus x, like that. Okay, and in that way, it more closely resembles the given function. So this would be our final result for number 5. Okay, now number 6, let's have a look. We have 5x multiplied by the cotangent of 8x. Well, this is a product of functions. We have 2 functions of x. So u is 5x. And what is its derivative? So I'm going to use uppercase u and uppercase v. So u prime then would just be 5. Now v is cotangent 8x. So what will v prime be? Well, let's check our formula sheet for the derivative of cotangent 8x. It's negative cosecant squared 8x times the derivative of 8x, which is 8. So negative cosecant squared 8x times 8. Or negative 8 cosecant squared 8x. Just like that. All right, so again, it was negative cosecant squared 8x times 8. So negative 8 cosecant squared 8x. Okay, and so now we know we're going to use the product rule. So let's go ahead and do that. So here we go. Oh, product rule, of course, is also on your paper. Product rule, so uv prime plus vu prime. U times v prime plus v times u prime, like that. So this is the same as negative 40x cosecant squared 8x plus 5 cotangent 8x. Okay? So in terms of common factoring, you cannot touch the trig functions. Their angles stay the same, but we can remove 5 or -5 as common from the front of each term here. So if I remove 5, this will be -8x cosecant squared 8x plus 1 cotangent 8x, like that. And that's perfect, although you might want to put the positive one first. So this would be the same if we did cotangent 8x minus 8x cosecant squared 8x. Same thing, just like that. Okay, but again, the key is you cannot common factor, you know, this 8x. It is the angle. The function has no meaning without the 8x here. Same thing here. You can't have cotangent of nothing. 8x remains the angle. Okay. Problem 7 here. Is that too usually I don't flip them over and write on the reverse side. Is that going to be visible enough? I think it might be okay. All right, let's try this one. So f at x is 6 times the cotangent of 4x. Find f double prime at 3. This means we need to find the second derivative. So we begin, of course, by finding the first derivative, which is called f prime at x. So what is the derivative of 6 cotangent 4x? Well, we need to know the derivative of cotangent 4x. Its derivative is negative cosecant squared 4x times 4. So we have negative 6 cosecant squared 4x times 4. Okay, again, the derivative of cotangent 4x is negative cosecant squared 4x times the derivative of 4x. The 6 remains in front. I took the 6 and multiplied it by the -1. Okay, so hopefully you're okay with that. You can keep going back and forth. We had cotangent 4x, negative cosecant squared 4x times 4. Okay, so this is now negative 24 cosecant squared 4x and that is just our first derivative, and we're going to be taking its derivative in order to find f double prime. Now, look, this function means chain rule, because it is the same as this, negative 24 times the cosecant of 4x all squared. And certainly written that way, you can see we're going to need the chain rule in order to differentiate this. Okay, so these functions, look, both of these ones, when you take the derivative of tangent or cotangent, you get a function like this. If you then had to form the second derivative, you will automatically need to use the chain rule because of the placement of that exponent. Okay, so again, this is the same as this. Now we use the chain rule to form f double prime at x. So what happens? The 2 comes forward and multiplies. The new exponent decreases by 1. And then we multiply that by the derivative of the inside of the bracket. What is the derivative of cosecant 4x? The derivative of cosecant 4x is negative cosecant 4x cotangent 4x times 4. Negative cosecant 4x cotangent 4x times 4. So simplifying this involves taking negative 48, multiplying it by -1, and multiplying it by 4. So let's begin. We're going to have positive 192 when we do that. And now look, we have cosecant 4x multiplied by cosecant 4x. So that's cosecant 4x all squared. And then we have a cotangent 4x. Okay, just like that. So we multiplied negative 48 by negative 1 and by 4. That's here. Cosecant times cosecant right here, and then cotangent. Okay, and now look, we're trying to evaluate when x is 3. F double prime at x, F double prime at 3. So F double prime at 3. So we put a 3 in here. So we want the cosecant of 4 times 3, or 12. And here, cotangent of 4 times 3, or 12. Okay, and then you would assume you would go to your calculator at this point. But we've got one more thing to do. So first, we've got to make sure the calculator is in radians. Okay, always keep it in radians for this whole unit, actually. Okay, and the other problem is we don't have a cosecant button. You see that? So we have to change these things. So cosecant is 1 over sine. Cotangent is 1 over tangent. So we can change this to 192 times 1 over the sine of 12 squared times 1 over the tangent of 12, like that. Okay, and now we should be able to punch that in. Okay, I might start with this part here, and then I'll multiply it by that, and then at the end I'll multiply it by 192. Okay, so I'm gonna do, can you see the calculator all right, hopefully? So I'm gonna do 1 divided by sine of 12 equals, so that's that number, but I gotta square it. Okay, so that's this part. Now I'm gonna multiply by 1 divided by the tangent of 12, okay? And lastly, I'm gonna multiply by 192, and this is our answer here. Okay, and I'm just gonna round it to 3 significant digits perhaps, and that would be 1, 2, 3, so negative 1050. Okay, that's just rounding to 3 significant digits, which you would need to be instructed how the rounding should be done. All right, so hopefully that was okay. We'll do one more together here, okay? So we have y is 2 times the secant of 5 theta. Find y double prime. So another second derivative problem. So as you know, we have to begin by finding the first derivative. So we take 2 and we multiply it by the derivative of secant 5 theta. What's the derivative of secant 5 theta? Why, it's secant 5 theta tangent 5 theta times the derivative of 5 theta. Now theta is the independent variable, so it's like du by d theta. So the derivative of 5 theta is 5. So secant 5 theta tangent 5 theta times 5. Okay, so the 2 is multiplied by secant 5 theta tangent 5 theta times 5. All multiplied together, so now we have 10 secant 5 theta tangent 5 theta, just like that. Okay, now that was to form the first derivative, but we want the second derivative. So how do we do that? Well, looks like we have a product of two trigonometric functions. We have to use the product rule. Now you can group the 10 in with your u if you want, or you can keep it out front. And what I mean is like this. You could keep the 10 out front. And then this is your u, this is your v. Okay, like that. So maybe I'll come to the bottom of the page here. So we can say u, so if I leave the 10 out of the picture, then u is my secant 5 theta. And v is my tangent 5 theta. So what is u prime? U is the derivative of secant 5 theta, which is secant 5 theta tangent 5 theta times 5. Maybe I want the 5 in the front. So 5 secant 5 theta tangent 5 theta. What about v prime? What's the derivative of tangent 5 theta? It is secant squared 5 theta times 5. So 5 secant squared 5 theta. Okay, so I've got my u, my v. Okay, u, v. I've got u prime, v prime. So I'm going to do the product rule right inside this bracket with the 10 outside. So u times v prime plus v times u prime. Okay, make sure you got that all visible on the screen here. Yeah, looks okay. Okay, so u times v prime plus v times u prime. So I'm just gonna simplify inside this bracket first. So this is 5, and now it's already secant squared multiplied by secant. So this becomes secant cubed plus, here we would put the 5 in front. There's a secant 5 theta. And there's also tangent times tangent, so tangent squared 5 theta. Like that. And that's pretty darn good, except we can common factor this. Look, we can pull out a 5 from each and 1 secant 5 theta from each. So those come out front and multiply by the 10 that's already there. So 5 is multiplying by 10 to give you 50. You're also multiplying that by secant 5 theta. So now if we divide this term by 5 secant 5 theta, we're left with secant squared 5 theta. And after the plus sign, if we divide this term by 5 secant 5 theta, we're just left with tangent squared 5 theta. All right, so I hope that's okay. We already had a 10 out front. So when we pull out 5 secant 5 theta, it just multiplied by the 10 that was already there. I could show you. The 10 was already there. All I did was pull out 5 secant 5 theta. Pulling it out from this term, it left us with that. And after the plus sign, pulling out 5 secant 5 theta from here, which means by division, left us with that. Okay, and then out front, you can make that a 50. All right, thanks very much for watching these 8 examples. There are recommended practice problems for you to try in your textbook, and we are now in exercise 27-2. Okay, I hope you guys have a nice day. Bye-bye.